Okay. Welcome to the talk on information theory. I will cover first informations of associated algebras, and then as a second part the use of differential brain diagrams, and as a third part I will give you the connection to physics. No.
That's something else. Okay, it's okay.
First, the idea and the motto of our case for deformations of associative algebras. I'll start with a picture. And tangent cohomology is equal to the tangent space of the moduli space. And here we have our space with the root action of S1. And the moduli space would then look like something of that form, and the tangent space to it would be similar to that directions.
So the moduli space is on the left and the cohomology is on the right.
Yeah. That's the root action that the moduli space as a whole. And this illustration will look at it in the case of associative algebras. And the definition is an associative algebra is a linear P from B tensor B to B, where B is just a vector space which satisfies the following.
Everything is over C, I guess, over the complex numbers.
A priori, I don't fix any field.
Okay.
And it satisfies Q, B, C, equals to the ring, AB, if I would draw this property with diagram, it would look like that. at least at this direct commute. Now I define a notion of equivalence, namely let mu and mu prime be associated with algebras. Then mu is set to be equivalent to mu prime if there exists a level from u to v bijective such that L times mu prime to v is equal to, that's the definition, that's the action of the group GLB on the associative algebra. Which is then equal to mu of the AB. Okay, now a small exercise. You can check that this action preserves the structure, the associative algebra. And so we can define, first of all, by notation, we fix S of B like that to be in the category of associative algebras over B. And we define moduli space which is equal, which we denote by such an example, which is defined as the associative algebras V modeled out by the general linear group action. And that's the first part of the Hochschild complex, but I'll come to that in the second part.
You mean it's tangent space?
Yeah. Now to other definitions. Once again, mu is an associative algebra. And mu1 and C2 of mu is then we define the action or the operations. U1 is ABC. U1 is And we define set2 to be the muse
Sorry, what's the subscript of the delta?
and mu is the mu I took here.
L tends to be is just linear maps.
Oh, okay. So
Oh
you,
yeah, yeah, and here yes, E2 will be
so you take mu and associative algebra, it's a function like that, and then u1 is just a linear map from the. Okay, so this is the option.
Basically, he wants to define the Hershey complex and motivate it by geometry. So he's taking a point on the moduli space, this mu,
Okay.
and he actually wants to know what is the tangent space to that. So he's gonna take a curve, but he goes before and gives you first the formula, but the point is to get the formulas out of the geometry.
Okay.
So we construct the given data is mu, mu1, and g, and I can this data are independently given, and you construct something to define something out of these three independently given data.
It's kind of like the I'll use it to define homology or cohomology.
So,
Yeah, and then afterwards we'll see that it corresponds to the tangent space as the geometric meaning, and later on we will define the Hershey complex as a whole, and that's just a part of it.
so basically, he fixes mu, and he takes arbitrary vectors mu1, and he wants to know when this mu1 is tangent to the moduli space. And here the answer is it's tangent when this is 0. So that, but, yeah.
Right. mu1 is not non-algebra structure, right?
It's just an ambient vector. So because when will we see this? It's just a bilinear map.
And maybe it's the role of g would be what?
We will see afterwards. It will be the tangent vector to the action, to an orbit. That's what it would be.
So when you have a G1 there, is it just G or in the second?
It's Q1.
All G's are G1?
Yeah, here, yes.
Yeah.
And also the first one, right?
So,
That's just the image of sigma mu applied on G, where G is in C1. Then we define the cohomology.
So here mu type could be mu1, right?
Sorry?
Here mu t could be mu1.
Yeah.
Okay. And G could be G1, yeah.
And now we have everything defined to prove the model in our case of that example. And we start with the lemma, which states that tangent space to the associated equal to the set 2 mu of, yeah, but I forgot to fix. These definitions are always dependent on the mu we choose. So there is and the proof. First, we think about the tension space, which is associated to the associative algebras, and it corresponds to curves. Yeah, well,
This is first S, right? Without modeling by the
first S.
As with the big R, with the straight R.
I'm asking if this is before taking. This is not the modularized space.
Yeah, and that's why you have a quotient for the homology. It's a quotient. So the homology means it's the infinitesimal version of the moduli space. But before taking the quotient in homology, you take cocycles, and the cocycle is the tangent space before taking quotient by the group action.
So that's the moduli space or not?
No,
No.
modular. So the definition of moduli space is after quotient.
Yes.
So here it's taking tangent space to the
okay.
thing which is.
Not disable.
So you mean that? Okay. Okay. I will continue.
And one another question. You are taking the same notation delta mu for first and the second action. Okay. But they are technically two maps.
Yeah, but this will be a quotient. Right?
Yeah, of course.
These for
Sorry?
when you have a complex, you call D to every map.
Yeah, we could add indices if you would.
Well,
Yeah, and tangent space is just the first order terms. Of the curve ut in associated algebra will be,
So that's a vector in the tangent space, right?
yeah. And the approach is just that we assume the ut is analytical. And so it looks like that. Yeah, of curve which passes through mu in t equals 0. Mu plus t mu1 plus t squared mu2 and so on. And now if one applies the relation I defined for an associative algebra, namely mu2 of mu t c equals mu of c, and inserts this expression, we can compare the first zeros, order terms, and so on, and we take the zero order partitions, you just get the equation for it to be an associative algebra. And if you take the first order terms, you get, well, I'll just write the left hand side first. An example.
There's a C, right? In the parentheses, you should also have a comma C.
Yeah. Now we take the first order terms. We get
So here you have also done that for the right hand side and move it to the left hand side.
I have separated the right hand side and left hand side.
So the minus signs come from the right hand side.
Okay, and this is exactly the definition of the sigma mu we find there. So we can say the first order terms of the curve we assume to be in SE corresponds to the tangent space, and this is exactly Z2 of mu, Z2 mu of VB.
So, as you wrote in the proof, you have to assume that you have analytic curves at the point where you're looking at. So you have this whole space, and you quotient your VX. So in general, you don't get a manifold. You get most very manifold, but then you still be voltage.
This is before.
Yes, but if even before the quotient there could be singularities. So in fact, this shouldn't be thought as a real theorem. In fact, this is a motivation for the formulas. So in the order of presenting, we shouldn't state it as a serious theorem. It's just to get.
So it's just some formal manipulation which gives us some motivation.
Yet it's to understand what is basically cohomology, and it's also used to define cohomology.
Works on the points, but so the associative structures on V is not manifold.
No, it's an algebraic variety.
Right. But it works on the points where it's
smooth.
analytical and it motivates the definition of that. That's the point, right?
Yeah, exactly. And you will understand why delta squared to 0. It basically means that the manifold is invariant by the group action. It exactly means that. The fact, yeah.
We will explain that,
Yeah.
right?
So then in the definition above, then you were with this delta mu, mu1 there on the bottom left board. So this is a minus there. This is not an equal there.
Oh yeah, that's minus.
Yeah. Sorry. Okay. Yeah.
Okay, and just for later, I'll also write down degree n terms for degree n equation we get. Well, it's only for later, so that we see the connection.
So this equals to 0.
Yeah. And now we assume that everything works smoothly. So especially for manifolds where we have a group action mix, we assume that tangent space element at the quotient is equal to the tangent space of the manifold quotient out by the tangent space of G times element X, where that would be just a submanifold. And we will get an idea of that by taking unequal associated algebras over V and G the general linear group of V and X the new group. So for our motivation, we just assume that everything is like in a good case, and it works. And now we want to show that, once again, only to give you an idea, that tangent space of mu of associated algebra, which is by definition the tangent space of the quotient, is equal to H2 of mu, which we define as
So the lemma is the equality of the middle, right?
yeah. So that's the definition here. That's the definition here. So the proof is once again quite similar to the other one. We assume that everything works smoothly. So in our case, we have to show, since we already know that the tangent space to mu at the associated algebras corresponds to that term, we only have to show, to prove it, that tangent space to the group times mu is equal to that term. So, you know, by the other lemma, that corresponds to set 2 of mu. So the claim is that mu is equal to
So your notation is the same for right action or left action. I mean, by this you mean the same action.
Yeah.
Okay.
And once again, the tangent space is just the curves, the order 1 of curves. And the form GT times mu for our GT is in GLV. Once again, we assume GT to be analytical and we write GT as analytical sum. And by definition, GT times mu is equal to GT. Is equal to T inverse times mu and if one writes it out, one gets for GT inverse something like an increment Q1 plus something else times mu and
So, what do you mean by GT inverse? Sorry? But what do you mean by GT minus 1?
it's the inverse, yes. The inverse of the curve inverted.
Yeah, but why can you invert?
Since we're in field.
Ah, okay, so it's for a value of t, you are in G and then you inverse. Okay.
Well, we are, I guess, we are just linear map from B to B, but we expand around that entity anyways. We have an open ball where you are.
So this is actually G.
G is GLV. Yeah.
No, but the G a priori is just a linear map from B to B, right?
It's small, which one? G1 you mean? Which G?
We define G to be GLV.
What, which G? Big G?
Yeah,
or-
it's not really GLV, right? It's the orbit under the action of GLV or EV. So GT, it's a priori just a map from V.
No, GT is a curve. Is a curve in this orbit. GT is a curve in the orbit. So GT dot mu, yes. So you have G at the big GLV, which acts on mu. This is a submanifold, and you take a curve in that.
GT dot mu is a curve, but GT itself is an element.
No, GT is a curve in the group which goes through the identity. A curve in the orbit which passes through mu is in fact the image of a curve in the group which passes through identity.
Okay. So he
So
has a
V
right to inverse.
goes-
Yeah.
Yes. Okay.
But so a priori G for a fixed T.
With G. There's many G.
Little T for some fixed T. Little GT.
Little GT. It's
It's
one.
an element from a linear map from B to B, but you make the additional assumption here in line 2 of the lower blackboard, right? That additional to being linear is also inverted. And that gives you the right to really invert.
GT is an element of GLV.
Yeah.
Yeah,
So
for
he
all-
takes a path and he writes that GT applied to you, where GT is an element of GLV.
Yes. We view GT as a curve in G, and when we
It doesn't have anything to do with the G1 we had in the
No.
No. Sorry.
but here the G1 is what you are thinking. Yeah.
Okay, so everything there. Sometimes it's just a bit confusing because your classes look like your keys.
Ah, yeah.
Yeah. Yeah. Then we take once again degree 1 terms. So if we take the identity on the left hand side, we get mu of G1 plus mu of
The other part?
Enough for us to see that and forget the right. That's right.
minus which is just the definition of the image of sigma mu on G.
Sigma, you mean delta.
Delta mu, yeah, sorry.
So what you're writing up there is basically delta mu of G1.
Yeah.
Applied on A and B. Yeah.
Okay, and that's the motivation for what will come afterwards. And we'll introduce the differential gradient linear loss. Where this whole part is then just some part of the cohomology. First, some definition. E is a graded vector space. If E is equal to direct sum over item set I. And if we take the tensor product of two graded vector spaces, and we look at the i's part, and it's just the sum of J plus K plus I, J tensor E, K. And
G plus K plus I.
okay. And category K map above it. K and P graded vector spaces, then a linear degree K map is a linear map path from A to B, such that f restricted to daily time is part of E I plus K. Now the definition. Let's denoted by brackets from E and where here are graded vector spaces. Yeah, degree 0 linear map. And grade derivation of degrees. Here, such that satisfies graded line, which is here AB plus minus 1 t times the degree of A. And the gradient here, is it of such that brackets are additional graded antisymmetric. And integrated derivation and so especially it satisfies the Jacobi identity since it has to satisfy that equation.
So the point of this way of writing it is to remember the signs in Jacobi, because otherwise it's very difficult.
Yes, you need also a degree part for ASP on the definition of antisymmetry.
But that's just a shorthand to avoid making lots. When it's on an exponent, it really means degrees.
Very useful yeah, it's just degree. And differential graded and yeah, short-term notation for grade here, Gatomar. Right here. GLA is graded here. Together with homological derivation that just homological just faster. Which figures forward. And if one has a defined probability algebra, solution in our current equation using the Lorentz polygon such that sigma polygon is zero. And even has fixed degree here, where one just writes MC of E as the elements which satisfy now.
Isn't there a help?
Yeah. Okay. Now come to the example. I'll probably have to next. Next solution example. The Gaussian model bring the other one. Yeah, is the greater phase. And the bracket action is defined as that bracket G and circle over G minus 1 circle over that. And that circle over G is defined as some I equals 1 up to the degree of f plus 1 minus 1 to the degree of 2 times the degree I plus 1. So call that IG, and this S would call it IG. Just insert G as we can check the body fineness, for example, to get yourself included with structure.
Sorry, so what do you mean with fineness?
Yeah, well, for example, that some here isn't in the wrong name.
Ah, okay. For the degrees.
Yeah, for degrees.
And what you mean exactly by inserting the isolate? Can you tell us in elements what you mean?
If we have F, we insert some elements, and we on the ice element we insert G of G's. So the ice argument F is G. And why is this important, or does it have to do with if they find a graded figure with us? Lemma says that there's somehow satisfies the open. So there's our PLA, there is these brackets. Integrated proof would need quite many complications, which I don't do, and if you want, can do it yourself.
So this indeterminate guys place is exactly the reason why you have +1, right? Because
Yeah,
somehow
yeah, exactly.
you lose an entry, and so you need to make up with a +1 and that would be
We say, because you say that it's indexed by n, but then contains 0.
Yeah.
And it starts probably.
You know, I think if it's solid, the orders are always 0.
The what?
The order of graded vector space. Oh, well, no, I mean, for I equals, if you, for I equals 0, it's just 0.
No, because, can you lower the markers? Because you have there a bit more. So you have there, this is the sum of i's, but I'm just wondering, if you consider that I is that 0 is a natural number, then in degree 0 you have a linear map from A to B. That's what we want, right?
You don't want linear maps from like K to K.
Yeah, there's not anything linear maps from K to B.
You feel
Wow.
you want to enter the space.
And you would get to start with interpreting a result of the you need some natural read to say which somehow destroys a V and it doesn't affect any.
Or you can just say that the bracket there is 0.
But if it's anyway 0,
Yeah, I think it's like that. You know, the reason that there is the interaction of this -1 over 3 zeros and -1.
Sure. So I think in geometry, it's like when you have vector fields, the Lie algebra, and you have functions, and you can add the functions to create a Lie algebra by doing a similar effect, because the function is a module of the vector fields. So here, if you want to have these things, it would mean to add, in this picture, to add like the function to the vector fields. And there's a precise meaning to that if we go super geometry. I think that's really the answer to your question.
I was just wondering if this is an opera.
If it's an opera?
Yes. I think you wonder that if it's an opera.
I'm not sure. No, it's not opera. It could be an algebra of an opera. It's clearly not an opera. Oh, you mean these circles?
Yes.
Oh, that's yeah. And you talk about that in Tamarkin's proof. That these brace operations, they are exactly this circle. So it's called the brace opera.
another lemma, which relates what we've done before with Mauer-Cartan equation, says that for the characteristic of our PK, where we assume it's a K vector space, and the characteristic of K is not equal to 2, then the Mauer-Cartan elements of the Gerstenhauer brackets, the Gerstenhauer B argument is equal to the associated algebras over V. And the proof is I recommend you to read yourself proof, since yeah, I mean, if you don't try to invert in some example formulas, then you probably won't get the grasp of it. So we insert new and new. Yeah, another thing we assume that the homological derivative is 0.
Sorry.
We assume that the homological derivative is 0.
Oh, there's no delta.
Yeah.
Okay. No, here he hasn't defined, in his definition, delta is 0 here.
And we only have a great differential, not differential graded theory.
It's just a graded algebra.
Yeah.
A differential graded algebra is a graded algebra with a differential.
Mm-hmm.
If your differential is 0, the graded algebra is a differential graded algebra.
Right.
So you can write the Mauer-Cartan equation, but basically it would only mean bracket alpha alpha equals 0.
Well,
Yeah, first I just insert the definition here.
And that's also why we want the shift. You mentioned the +1 shift. To get the right degree for this word.
Then if you write that on element, it looks like that. Oh, right, you didn't mention that the solution of the Mauer-Cartan equation is an alpha such as what? An alpha equal to 1, right?
Ah, yeah.
Yeah. So by the definition of associative algebras, we have that the Mauer-Cartan equations are associative algebras. And another lemma.
Maybe I can make a remark here.
Yeah.
Is that this thing that the space of structures is Mauer-Cartan? It works basically for most of the structures you will see in reality, and to prove that, one can use operands to produce a graded algebra. And the tool which from a type of structure gives you this graded algebra is Cauchy duality. So when you hear Cauchy duality, it's exactly to arrive to that precise point. Cauchy. K-O-S-E, Koszul.
I don't know what it is.
It's French actually, but the name is.
And it's like you also say Kazan.
That's P. We are going to the other one. And alpha and now quantum element of the great periodic one. Then the answer alpha is the great periodic. Okay, what we have to show? We have to show that first, and alpha is derivation. And that is a homological derivation. By definition, that by two elements equal to alpha into, and since alpha is integrated here, therefore we have the Jacobi identity. Which is equal to this definition of derivation. And then alpha squared on the element equal to alpha. This is once again by the Jacobi identity equal to alpha. That's zero by the gradient density symmetry. And
Are you sure?
But not of the phone equation.
Yeah, but is it?
yeah, but now.
Yeah. It's a, if it's given by a gradient symmetry, it will be zero, but here it's odd, so it's the other argument.
So we have that this is equal to minus that.
you know that it's a homological derivation. We come to the third part, connected with physics.
Oh, no. I mean, what's the point of all that?
Here we have to find the delta.
Ah, okay, so we should put it as a definition, right?
Yeah.
Oh,
So eat the breakfast and alpha where alpha is in our carbon equation is the function.
so basically, if you take E to be what is up there, so the one on the upper left corner, and for alpha we take mu and associative algebra, right?
Yeah.
We have seen that associative algebras, they are the more carton, right? That's the lemma. No, is it the lemma?
Yeah.
Yeah. So we know that an associative algebra is such an alpha more carton. So we can take add alpha, and this defines a complex. I mean, differential. And the claim that we have to do, it should be a check that these formulas that we get coincide with the one we did through deformation theory at the beginning. So basically, by deformation theory, we can discover what should be the cohomology in degree 1 and 2. But in order to generalize to arbitrary degrees, that's a good way to do it because the add alpha is defined for every guys in E. So for arbitrary EI. Through deformation theory, we have defined for E1 and E2. We don't know what it is for EI general, but through this, we know what it is in general. So that's why brackets are very important, these GLAs, because they can really get the whole cohomology.
And the exercise that P of degree 1 and then calculate sigma mu. You can do it for yourself. Minus mu of P minus mu of P. Then sum minus 1 of P. Which is then exactly the terms we got before by applying the mu. Which corresponds to the definition in chapter 1.
I think at the end, the alpha and the A should be the same, where you get the Fourier density. Here. No, one up. Yes, and at the end. Go further to the right, go further to the right.
Oh, yes. Yes. How the last term is equal to the one which is below? Up there, the first line of computations. If you take the last term,
Yeah.
yeah, yeah, that one, yeah.
I mean, your
You're
definition of
yeah.
graded E algebra was that flexible equation.
Yeah.
There's no point.
So just look at the last term and the one below. Are they really equal? And then you will understand. Or once again, what is to be yeah, what was your yes? Yeah.
So that's the first thing, and then the second one I don't get yet. So you compute this, and then you say, okay, this term is the same as minus, but the minus one, it's a multiplication. Okay. So 1 plus 1 is 1 times 1. Okay.
Now finally we come to the third part. Connections with physics. First on this page, I don't know whether I should write it down and put it right down.
What do you do?
What I say.
I don't know, but also you mentioned at some point that you kept for further later use the terms of degree. Have you used it, or you want to use it?
No, I forgot to use it.
Okay.
Yeah, as a remark, in one proof we took the degree n elements of a curve, and this exactly corresponds to the sigma mu, or to the sigma we defined here.
But do you plan to write exactly what it means for this curve to be in us in terms of the bracket and delta? So, do you plan to write the deformation? Okay. I thought it was for that you wanted. Okay.
So what sigma mu?
The deep delta mu.
First of all, Lewis and Richardson which showed that the Gersten-Haber differential after Gersten-Haber showed that the Gersten-Haber differential algebra is a differential gradient algebra. They used his work to axiomaticize all this stuff into deformation theory, and they only
But sorry, did you prepare that part or not? No, okay. So no, you shouldn't do it. No, I was planning to do something afterwards, but not directly that. It's fine. Okay. So I think your talk is over here, right? Okay.